So after the pleasure that was assignment 23, we now come to step support assignment 24, which is less so. So we're asked to integrate this horrific looking thing. Now the first thing I spot is, well, here's a compound sine thing. So I'm probably going to need the compound sine formula at some point, where you distribute the angles out into sine, cos, and swap them around in each time. And I also see this cosec. Now I need to remember that cosec is 1 over sine. Okay, now I to the in is just when you put n in here. So that's just, I've just copied out this. Now, I should explain this. I'm so terrible at integration that I literally need to color in the dx's every time I write them, because otherwise I'll try and cancel it with another x somewhere. So that's why that's green, and it will be the entire video. In minus 1 is just when you put an n minus 1 into the single place where you can put an n, which is just there, so it's n minus 1 there. Now, when you expand this out, nx minus x plus a half x is nx minus half x. So that's good. Now, it's asking us to evaluate in minus 1. So let's do in, which is this, take away in minus 1, which is that. So let's just do that, take away that. So I haven't done anything new here. I've just taken that thing, and I'm taking away that thing. Now, when you have two integrals and you're doing them over the same limit, you're allowed to just put those together. So instead of having two integrals here, I'm going to have one integral here, and I'm just going to write the whole thing out with the minus and then just the other one. You'll notice I've colored in some stuff here, and that's because this is a factor of this term that's also here, and this is a factor of this term that's also here, so I can factorize those out and leave behind just the two compound sines. Okay, so that's looking a bit better. Now I've colored in those because you know at this point I'm going to use this thing here. So I'm going to distribute out the a, so it's going to be sine a cos b, so sine nx cos a half x plus, and then you swap them around, so it's sine of a half x cos nx. And I've just done the same thing here, and I put it all in a bracket because the next line I'm going to do is I'm going to expand out this bracket, so it's minus this one and then plus that one. Sorry, and then minus that one, I should have said. So I've just expanded out the bracket, minus that one, and then minus that one as well. Okay, well now I see some cos of minuses and stuff, so now I need to remember that cos is an even function. If you put in a minus x, you just get the same as if you had done cos x. So this I can just say as cos of a half x, because cos is even. Now sine of minus a half x, sine is an odd function. So if you put in a minus, you get out a minus. It's the same as minus sine of x. So this here isn't sine of a half x, it's the same as minus sine of a half x. But the minus will cancel with that minus to give myself a plus. Okay, and that's all I've done with that line. Well, now I see sine nx cos a half x minus sine nx cos a half x. That cancels, which is great. Sine a half x cos nx plus sine a half x cos nx. That's two lots of those things. So that's good as well. And now I've highlighted these two things red because remember, finally I use this one. Cosec is 1 over sine, which means this is just going to cancel with this. This is 1 over sine of a half x. This is sine of a half x, so we're just going to cancel them. And we're left with this, which is good. Just because I don't like this half, I'm going to move this 2 and distribute it out into this bracket, just to make that pi minus 2x into this cos nx. Okay? And this is looking much better. Even as someone who hates and can't do complicated integration, I kind of look at this and think, yeah, I could probably do that. Like this seems okay. I'm going to expand out the bracket here to give myself pi cos nx minus 2x cos nx. And now I'm going to split this up. The opposite of what I did earlier, I'm going to split that up into two integrals. I'm going to move the constants as well out to the front because constants don't do anything to an integral. So I'll just split it up into two integrals there. Okay, now this I look at and think, great, I can do that. I can integrate cos nx. Cos integrates straight to sine, and then I'm going to have to divide by an n. Because like if I was differentiating, I would times by the n. It would be n sine nx. It would actually be a minus, wouldn't it? Because cos differentiates to minus. But if you integrate, you would then divide by n. So this integrates up to sine and then divide by n. I haven't touched this yet. This thing here, when you put in a 0, sine of 0 is 0. So nothing is going to happen when I put in the 0. But when I put in a pi, that's quite interesting because then I get sine n pi. Now n is a positive integer, like 1, 2, 3, and so on. I'm sure you've learned to count. So what happens when you put in a positive integer of pi into sine? Well, sine of pi equals sine of 2 pi equals sine of 3 pi, and they actually all equal 0. Think about that sine graph that goes up and down and up and down. The roots of the graph are always at pi intervals. They're pi, 2 pi, 3 pi, 4 pi, and so on. And you can sketch it out to convince yourself of that, but those are all 0. So when I put a pi into here, I get 0. When I put a 0 into here, I get 0. So all of this is just 0. And I'm just left with this. And I'm pretty happy with that. I'm so happy with it. I'm going to put it in a box because I've done such a good job here. And then I would move on to the next step question. No, I wouldn't have even attempted this one. But this is still an integral, so I need to deal with this. So let's go on a quick detour now of how to deal with this integral x cos nx. Now I've colored these in, the two different colors, because I'm going to use an integral by parts here, an integration by parts, the rule. So the rule is if you have two functions, g of x and f of x, and you're integrating g of x and then the differential of f of x, you have gx f of x minus g dash the integral of g dashed f of x. So in English, what this means is if I choose g of x to be x, I'm integrating x, and then notice here this blue function, that's cos nx, I want it to be at least, but that's f dashed of x, which means to find f of x, I need to integrate this thing here. So if I want to make that an x and that a cos nx, I need to integrate this to find myself f of x. Like, this is fine, this g of x is still just x, and g dashed of x is 1, but I need to integrate this thing here to get myself f of x, and that integrated is that. We've already done it already. It's just there. So I integrate it and put it here, and then again it turns up here as well, so I integrate it and put it there. Now this is fine. That's just x sine nx over n. This here integrated, sine integrates to minus cos, and then again you divide by an n to get over n squared. And then I've got a plus c here. That's not going to end up making a difference. When you integrate, you should typically have a plus c, but notice how when I get to my thing, I've got limits on mine, so I'm not going to use a plus c. So, but I'm just putting it there for correctness. Anyway, these two negatives cancel, and I end up with my formula, which is to integrate that thing there, which is what I want to do. You get this thing here. The c is irrelevant because I've got limits to mine. So I'm just going to put this in here, straight into there, and I'm going to do it between pi and 0. Okay, so I'm going to put pi's into here, so all of the x's become pi's, and then I'm going to take away all of the x's becoming zeros. Now, lots of this is going to be good, right? So we've already looked at sine n pi. When n is a positive integer, all of that is just 0. So that term there is 0 because that bit is 0. Sine of 0 is 0, so that's 0. Cos of 0 is 1, so that's actually going to stick around. Now, what about cos of n pi, where n is a positive integer? So let's list them out. Cos of pi is minus 1, that's 1 pi. Cos of 2 pi is 1. Cos of 3 pi is minus 1. Cos of 4 pi is 1. Imagine the graph again in your head. It starts up at 1. Cos of 0 is 1. Then it goes down to minus 1 halfway along at pi, and then back up to 1 at the end of the first cycle, which is 2 pi, and then down and then up again. And so we've seen this kind of pattern in step before. We notice the even numbers make a positive, and the odd numbers make a negative. Well, what does that remind us of? Well, it reminds us of raising minus 1 to a power, right? Minus 1 to an even number makes a positive, and minus 1 to an odd power makes a negative. So cos n pi is minus 1 to the power n. So I'm going to put that into there. And this, again, like I said, was 1 over n squared. Now this negative I can get rid of if I swap the signs on these two. So if I just swap the order of those and swap the signs of them, then I can get rid of that negative, which is good. And now I can take out the n squared, and I end up with my formula for in minus 1. And that's actually the answer. This is one of those tough times in step where you look at this and you think, is that really the answer? Like, do I not have to do more to that? But that is the answer. There's nothing I can do to this, really. Now it says, and hence evaluate in. Now, if you see hence, and it doesn't say or otherwise, you have to use the hence, right? Even if you do something else incredibly intelligent, you're not going to get anything. You have to do the hence bit. So it's asking me to evaluate I to the in, but I have to use this. I have to use what I just found out. So how am I going to use this? Well, this is tough. I mean, I didn't spot this. I used the mark scheme. But in the prep, the prep that you did before this question, the prep had loads of like trig in it, had a bit of integration in it, a bit of integrating trig in it, and then it had this random question, right? This thing about a sum with some k's. And okay, well, let's do this, right? So you start with k as 1, so you get root 1 minus root 0, and then you go to k as 2, so you add in root 2 minus k root 1, and then you put in k as 3, and you get root 3 minus root 2, and then you go all the way up until you get to like n minus 1, where you put in n minus 1, and then you get n minus 2, and then you put in n, and you get this. But what happens here? Well, you might have already seen it, right? This root 1, take away root 1, so those go away. Root 2, take away root 2, those go away. Root 3 would go away with something around here. This would go away with something, well, this goes away with that, but this would go away with something earlier. This goes away with that, and we're just left with root n, right? And this is what we call a telescoping series. You start out with a ton of terms, and they just all go away except for the first and the last. Imagine a telescope folding in itself, right? You only see the first, the end bits when it's folded in, right? Everything else just goes away. That's why it's called a telescoping series. And somehow, we have to make this into a telescoping series. So I have to start with IN. I'm being asked to evaluate IN. So I start with IN. And I mean, I guess the only hint for this was this bit in the form of a sum. Like, telescoping series come from these sums here. So when you see that, maybe you think, oh, maybe I need to do some kind of telescoping sum on this. But here's my telescoping sum. It looks like, and wait for it, there it is. So somehow you were supposed to come up with this. I certainly didn't. This comes from the marks beam. But IN minus 1, well, this here will cancel with this here, right? And this here will cancel with this here, and this will cancel with this, and you go all the way down until this cancels with something earlier, this cancels with that, and then this, and then I have this kind of thing at the end there because I need something to cancel with that, right? So all of this will cancel, and I'm just left with IN equals IN. So this series is good, right? This series definitely works because it's just IN equals IN. It's a very complicated way of writing IN equals IN, but it is a way of writing IN equals IN. Now, why have I done this? Well, because I've done it because look at all those things in the brackets there. I have a formula for all of these things, right? And this is where the hence comes in. I have a formula for each of these brackets. It's just this here, right? So let's get into that then. So here's my lovely expression, telescoping series. Here's my formula. So the red bit here, that's going to become this, just using n. So that's just the formula as it is. When I have n minus 1 as my first term, this becomes an n minus 1, and so does that. When I have an n minus 2, that becomes an n minus 2, though I haven't written it. Now I go all the way down to the end, where if I have a 1 there, then that becomes a 1, and so does that. So I have a 1 here and a 1 there. And then I have this spare I0 term at the end, which is just there to make sure this goes away in the original kind of series. Okay? But now, leaving your answer in the form of a sum, notice how all of these terms are identical. They're just using increasing powers of n each time. This one uses an n of 1, the next one would have been 2, then 3, then 4, all the way up to n. So that's a sum, right? It's a sum going from 1 to 2 to 3 to all the way to n minus 1 and n. So I can write it like this, where I have the sum from k as 1 to n. You can choose whatever letter you want here, where we start with k as 1, that would give us this term, then 2, then 3, then 4, all the way to n is our first term. So this is kind of written backwards, but I think you can see what I mean. It doesn't matter whether we write this way around or the other way around. Of course, we just have the I0 left on the end here. So this is looking good now. It's almost done, except we should probably evaluate I0. That, I think, is all that's left to do. So we just take the original integral here and just replace n with 0, and we get this. So the only things to replace are there. In fact, that's the only place to replace. Of course, this just becomes sine of a half x. But sine times cosec, now cosec is just 1 over sine, right, by definition. And so sine of a half x times cosec of a half x just cancel out. They just multiply to make 1, right? They just cancel there. So that's excellent. So now we just have to integrate a half of pi minus x, which is super easy to integrate with respect to x. It's just going to be a half of pi x minus x squared over 2. And then we just need to put in 0 and pi, and we're going to get a half pi squared minus pi squared over 2, which is just 0. And then, of course, minus 0 just all goes away, this goes away, and I0 is 0. And so we can just get rid of that, and we'll end up with IN is this here, which I hope is the correct answer. Thank you so much for watching, and I'll see you next time.